Hello everyone. Today we are going to see about the heat conduction equation, that is derivation of one-dimensional heat conduction equation taking into account the heat generation as well as the change in kinetic energy. So step by step here I have an explanation for you. Hope this will be useful for you. I'm going to take an object. Okay, a 3D object. In that I'm going to take a small element of infinitesimal thickness, okay, at a distance of x from the 0 coordinate, that is x coordinate. Here I'm taking from a distance x a small element which is having a thickness of delta x, right? Let me shade this element so that you are able to see that distinctly. Now assume the length of the element extends towards L in the x direction, and we are not worried about the y and z direction because this is a one-dimensional heat conduction equation, right? Now the heat that is entering, our concentration is only for this element, right? I have considered an infinitesimal small element, meaning a very small element, okay, of thickness delta x, right? Now the heat that is entering into this element, let me take it as qx, and the heat that is exiting out of this element, it is qx plus delta x, right? Now we are going to write the general heat balance energy equation. Heat balance equation. For this case, it is going to be qx minus qx plus delta x plus heat that is generated. Okay, inside this element, the heat that is generated, that will be equal to change in internal energy of the element, right? So change, when I say change, it is always with respect to time. So change in internal energy with respect to time. Right? Now, simplifying this further, the first two terms remains the same, no difference at all. Look at the next term. This is the heat per unit volume, right? So for the entire volume, I'm going to multiply it with the heat generated with the volume. Okay. That is equal to E is always mCp delta T. So I will write here mc delta T divided by delta T. The capital stands for temperature and the lowercase t stands for time, right? Simplifying further, volume can be written as area into thickness, right? So area into, since this is a thickness of del x only, so here I am taking del x, and here mass is always density into volume, right? So density into volume, remain, other things remain the same, delta T divided by delta T. Now again a small change, this volume can be written as the same way, area into thickness. So rho into area into thickness into C into delta T by delta T, right? Now let me divide this whole equation by A into delta X. I'm doing this, right? And I'm reversing the these two terms. So it is going to be 1 by A. Inside it is going to be Qx plus delta X minus Qx divided by, this is A, okay, plus what will we get here, the A into delta X will go, so it will be Q dot, here again A into delta X will go, so rho into C into delta T divided by delta T, right? Now further simplification by Fourier's law of heat conduction, I can write this term as minus 1 by A dou by dou X minus Ka dou T by dou X plus Q dot equal to rho C dou T by dou T, right? Now the negative and negative will cancel, A and A will cancel, so we will get dou by dou X, K into dou T by dou X plus Q dot, this is heat generation, plus rho C delta T by delta T, right? Now, in this term, we know what is this K. This K is called as thermal conductivity. Right? This is heat generation. And of course, we know constant density. And C, we know it is specific heat. Right? Now, in this equation, if K is taken as a constant, how will this get modified? This will change to, I'm taking this dou inside, dou square T by dou X square plus Q dot divided by K, that is equal to rho C by K into delta T by, you can write it like this also. Okay. Now, in this term, rho C by K is defined as 1 by alpha, where alpha is called as thermal diffusivity. Alpha is represented as thermal diffusivity. That is the amount of heat that is able to get diffused through a particular element. Okay. Now, our master equation has become like this. Dou square T by dou X square plus Q dot by K equals 1 by alpha dou T by dou T. Right? So, this is the master equation. Now, making modification to this equation will give you three other simplified forms. Suppose the problem that we, in any type of heat conduction problem, the first step is always to treat it as a steady state. Steady state is the variation of properties with respect to time remains the same. That is, they do not vary with respect to time. So in that case, the term variation of temperature with respect to time will be 0. So I can write dou square T by dou X square plus Q dot by K will be equal to 0. So this is the steady state form of the simple heat conduction equation. Suppose you are not taking this value as 0 and you're also studying the properties with respect to time, then you call it as transient state. Okay. So in transient state and without heat generation, so the general equation will change to, so this is your heat generation term, this will go away, right? So you will get dou square T by dou X square plus, you won't be getting the second term, right? So that will be equal to 1 by alpha, because it is transient. You have your variation of temperature with respect to time. That's all. Then next you have the third condition, that is steady state and no heat generation. Right? So in that case, look at the steady state means this right hand side will go. No heat generation, the second term will go. So what is left? Only the first term is left. Right? We are going to write only that now. Dou square T by dou X square is equal to 0. Fine. So this is the simplified general heat conduction equation. A short recap of what we have derived. We'll see that. We have taken a solid object in that we are forming a small element of thickness delta x, and this element is at a distance of x from the origin, and the thickness of the element is delta x, right? And we know the main properties, that is density remains a constant, specific heat C also remains a constant, and the variation of temperature with respect to time is also considered. Okay, now when you look at only this element, you can see the small element, right? So looking at this element, the heat that is entering into the element difference the heat that is leaving the element, so it is qx minus qx plus delta x plus heat generated, the heat that is generated inside this, so it is q dot g equals change in internal energy. So this is the simple balance equation, right? So I'm writing this. The next step is Qx minus Qx plus delta x remains the same, and this into volume. So Q dot into delta V, that is equal to energy is always, here I will write energy is mc, right? Delta T. So it is mc into delta T. Here it is change in energy. So that's why you have change in energy with respect to time. You have the delta T, that is time, at the denominator. Okay, now the first two terms on the left hand side remains the same. I'm expressing volume in terms of area into thickness. Area is capital A and thickness is delta X. Okay, then mass is density into volume, so rho into V into C into delta T. That's all. Again, here I'm substituting the volume, replacing volume with area into thickness. I'm dividing the entire equation by A into delta X. So hence it's finally modified to dou by dou x of k into dou t by dou x plus q dot, that is equal to rho c into dou t by dou t. Now this is the condition when thermal conductivity is going to vary. But we are considering a same material, so there is no change in thermal conductivity. So I am taking it outside because there is no variation, right? And then dividing the entire equation by k. So here I can write it like this. K, and also k is a constant. If it is varying, then I can't do this, right? So we have taken K, this thermal conductivity as a constant. So I'm dividing it. And here you can see another term which is introduced, that is called as thermal diffusivity. Thermal diffusivity is K by rho C. How much of heat can be diffused through the solid material of thickness delta X. Okay. Then after obtaining the basic heat conduction equation in one dimension, we are going to make some simplifications. Okay, to get the other forms, that is the first one is steady state, where dou t by dou t is equal to 0, right? So this right hand side term will be deleted. So you get only the left hand side of the equation. The second condition is transient state without heat generation. So when I say transient state, it is, you'll be having the variation of temperature with respect to time, but there is no heat generation. So the second term has gone away. And the third one is steady state without any heat generation. So here you see it is dou square t by dou x square equal to 0, right? Now, in our next lecture, we'll be taking this dou square t by dou x square equal to 0 and find out the equation for the temperature distribution in a plane wall. We are taking a plane wall, and that is only in the x direction. The thickness will be considered, that is, say from 0 to L, the thickness will be taken as x. For this, we'll find out the temperature distribution equation, right? So for this lecture, I'm done with. If you have any doubts, kindly post in the comments.